Okay, aloha everybody, and thank you for joining us for the Theme 15 session. Today we have the pleasure to hear about fire and specifically how people throughout the world who have faced fire for a long time, studied fire, observed fire, and had their ways of dealing and managing fire over the years from different places. We have 4 speakers here who will introduce themselves, but they will talk about fires in the context of different locations. We'll be covering examples from New Mexico, from California, from the far higher latitudes, and then from the Pacific Rim and Hawaii. And with that, we'll get started. The speakers will go one after the other. They will introduce themselves, and then we'll have about half an hour for questions and answers at the end. And we'll go.
Thank you. Is this your phone?
You can take your mask.
Good afternoon. My name is Chris Rose. I'm a professor of anthropology at SMU in Dallas, Texas. I'm an environmental archaeologist and pyrogeographer, which is one of my favorite neologisms, especially as it relates to fire. And I work mostly in North America with indigenous communities to better understand long histories of fire management, and I'm going to share some of that with you today with my work with the Hamish people in northern New Mexico. Now, an important part of our contemporary wildfire problem is that we tend to think of our landscapes as ahistorical, lacking a history of fire that's shaped the very things that have attracted us to these same places. We imagine that we can live in these places without history and without fire. Now, as an environmental archaeologist, I think it's equally problematic that we've overlooked the long human history in these fire-prone places. This photo from the 2003 Enso fire is just outside of Taos, New Mexico, and I think it encapsulates some of these issues well. Right? This is undoubtedly not the first time that Native people sat on the roofs of their homes and watched the watershed around them burn. But in the 1,000 years that people have been living there, this is undoubtedly the hottest and most severe fire that they've ever watched happen because of more than a century of fire exclusion. So what can we learn from the long experiences with fire of indigenous people? How did Native people manage fire and fuels in ways that allowed them to coexist with wildfire? I concentrate here on the dry forests in the southwest US, dominated by ponderosa pine and related species, mostly at elevations between 2,100 and 2,300 meters above sea level. Ponderosa pine forests have one of the best known historical fire regimes in the world, due in part to the fact that fires only rarely killed mature trees. Instead, some of those trees were damaged when they were younger at the base, enabling the fires to be dated using tree ring methods. As a result, because of several thousand such tree ring records from across the Southwest, we know that the history of fire, at least for the last, say, 500 years, has been one characterized by low severity fires, meaning low tree mortality, that occurred every 3 to 15 years per stand, usually during the arid foresummer before the summer monsoons hit, and that there's a very strong relationship between things that drive interannual moisture patterns. So there are strong relationships with El Nino Southern Oscillation, for example. Now, of course, that's not how fires burn through these forests now. Now, fires burn through the canopies of the trees with high mortalities, leaving big holes in the canopy. In many cases, like you see in the picture here, with no living trees to provide seeds for the next generation. And this is a crisis that's increasingly recognized, where our forests in the Southwest are increasingly being converted to non-forest vegetation as a result of unusually large and severe wildfires. Now, one of the big culprits in these drastic changes in the fire regimes has been more than a century of fire exclusion. And I point the finger, as he's doing here, at Smokey Bear for so effectively convincing us that we could live without fire, and in the process ensuring that we have to deal with more fires, more dangerous fires, more severe fires. Smokey's position never was realistic or tenable. We cannot live without wildfire or smoke, but this leaves open the question, what kinds of fire and smoke do we want to live with, or can we live with? This is a difficult question for us because we don't really know what our options are. Now, one of the reasons that we can learn so much from indigenous experiences and cultures of fire is that they help us to populate a menu of options for doing this, rather than having to reinvent the wheel. And so what I want to do is share with you a collaborative project with scientists from SMU, Harvard, University of Arizona, U.S. Geologic Survey, and the Pueblo of Jemez in the southwestern Jemez Mountains of northern New Mexico. And here we're working in what we call an ancient wildland-urban interface, where indigenous populations of Hamish farmers coexisted with fire and population densities that are analogous to the modern wildland-urban interface, or WUI. It's a weird word, I'm sorry. This term WUI may be unfamiliar for folks here or on the Zoom audience. It basically is a category of low to moderate density residential development within or adjacent to wildland environments and fuels that's particularly difficult for fire management because this is where the greatest hazard to human lives and property is concentrated. Furthermore, the physical ownership and administrative geography of the WUI makes it very difficult to enact many of the preventative measures that we know work. This is a fundamentally interdisciplinary project. You might go so far as to call it transdisciplinary as we worked across these many disciplines. We combined archaeology to study the timing, size, and location of human populations in this ancient WUI. We conducted ethnography with Hamish people to understand their cultural values of smoke, wood, forest, and fire, and dendrochronology of living and dead trees to reconstruct fires, climate, and forests around Pueblo settlements. Geoarchaeology, which is mostly what I do, to reconstruct multimillennial histories of forests and fires around settlements, and ecological modeling to evaluate forests and fire histories under different hypothetical land use and fire management scenarios, and to tie everything together at the landscape scale. So to give you a general idea about the archaeological and cultural context, since this may be particularly unfamiliar in this audience, ancestors of Hamish people lived in ponderosa pine forests in the southwestern Jemez Mountains for roughly 6 centuries between 1100 and 1700 CE. These areas were a true ancient wildland-urban interface between about 1325 and 1650 CE, when populations were between about 10 and 20 people per square kilometer. That would be mapped as WUI today by the federal government. The red outline here indicates the area of the ancient WUI. Tree ring sites are in white, the white dots there, and the black hatched areas indicate the geoarchaeological watershed sampling units. And now, rather than doing a traditional science talk where I kind of walk you through the results from each one of these project dimensions, I'm going to focus on some take-home lessons and our inferences about Hamish fire management, and then provide some of the evidence that supports those inferences. One observation about the ancient WUI was that these communities were fire-wise. Here I'm referring to an American wildfire protection program that advocates creating defensible space around your home in the WUI by managing both fuels and flammability, like you see on the figure on the right. Now, for the ancient villages and towns, we sampled all of the oldest wood on a half a dozen of these large Pueblo sites and up to 200 meters away from the Pueblo. And none of those trees were alive when people were living there. This isn't a limitation of the method, say the age of the trees, that's as far back as we could go, because if you go further than 200 meters, you can find plenty of trees that were alive when people were there. In fact, they're actually recording fires while people were there. But it does mean that the area around these communities was basically denuded, right? The coarse fuels were taken down and removed around these communities. Add to that thousands of feet trampling fine fuels, and then the harvesting of wood. Remember, these are people living at more than 2,000 meters elevation. The nights get cold, the winters get cold. They have to burn a lot of wood at home. That would have progressively thinned the forest, kind of as you move out from the village. And you get something that's very much like the classic Firewise scenario. We know that Hamish people managed both fire and fuels. Now, this graphic comes from our ethnographic work that documents at least 27 uses for fire and wood fuels that are scaled to different parts of the cultural landscape, from the home to the village to the agricultural landscape to the woodlands and forest between and beyond those. Note that most of these are about wood fuel uses. But we know that they were managing fire by the increases in charcoal deposition across the landscape during the period of Hamish settlement. That's the blue zone in these plots here on the left. This is standardized by the late Holocene mean and standard deviation, which indicates above average or near peak deposition from 1100 CE onwards relative to the last 4,000 years. But these fires were overwhelmingly small and low intensity. Now, one way that we know that is from an innovative study using optically stimulated luminescence of pottery on the surface of a site within the Hamish Wui. Now, here, all ceramics that were burned in a 2012 planned burn had their luminescence reset by the fire, but ceramics that were exposed to more than a dozen historical fires, and here the white dots are tree rings again, so more than a dozen historical fires, none of those were ever reset by any of those fires, indicating that the total heat exposure from a cool season planned, generally low severity prescribed burn was hotter than any fire than those experienced during Hamish management and immediately thereafter. We know that these fires were small also from a curious feature of the tree ring record. In the middle, we plot the number of fires per decade in gray and the total sample depth as a red line. Although it kind of appears that there were fewer fires during the Hamish period, but this is largely due to a shrinking sample depth. Right? We lose older and older trees as you go back in time. It's a fading record problem. So scale to sample depth, right, there's just a lot of fire, and it's more or less continuous. But the black bars are large fires, fires that scarred at least 25% of all the trees. And note that there are no large fire years at all during the period of Hamish fire management until 1650. Only after 1650 do you start to see this mix of small and large fires represented by the gray and black bars in that figure. This is corroborated too in our modeling. Here we compare a scenario with no people, that's the null model indicated in gray, and a scenario of intensive land use in orange with both a lot of fire use and a lot of wood use in the intensive model. I highlight the period of the ancient Wui here with the blue boxes. During this time, fires were much smaller, even if the overall area burned may have increased. Notably, both fire intensity and tree mortality were much lower during intensive Hamish fire management compared to the null as well, because there's less fuel. Now, this management of intensive wood use and many small fires resulted in a weakening of fire-climate relationships as well. These may be weird things and unusual plots. These are called Superposed Epoch Analysis plots, or SEA plots. These display interannual fire-climate patterns. SEA does this by isolating the climate values for event years, in this case fire years, which is year 0, and the years before, those are the negative lag years, and after those events, in this case, like I said, fire events. And then it tests them against a bootstrap resampling of random event years of the same overall sample size across the data set. And what you see here is that the classic, or we call the canonical Southwestern fire climate pattern holds. I alluded to this before when I was talking about El Nino, La Nina relationships with fire. across the Southwest, you see this pattern of wet years before the fire, anywhere between 1 and 3 wet years before the fire, and a really dry fire year. And what you see in this at the top is across the entire mountain range. And then in the middle and the lower, those are different sized stands of trees within the Jemez Wui. But this is after Jemez fire management. So this is after Jemez populations had collapsed due to colonial pressures. During Jemez fire management, those fire-climate relationships are virtually absent, right? At the stand level, and this is repeated at numerous stands across the ancient Wui, there are no fire-climate relationships at all. When you scale this up to the entire mountain range, when you've got a mix of local stands that have no climate relationship and those that are more distant that have climate, you still see drought as a significant driver. But nevertheless, this is a significant dampening of fire-climate relationships during Jemez management. Perhaps one of the most poignant lessons from Jemez is that we need to find positive cultural values for fire in order to live with it. This statement comes from our Hamish collaborator and two-time governor of the Pueblo, Paul Tosa, and this highlights this. Paul told us that fire adds richness to the land. It doesn't subtract it, doesn't destroy it, but it is something that requires great care and respect, but it's also something that can add value. It can support cultural and ecological values if we could work out for us what exactly those are. So to recap some of the lessons from indigenous fire management in the ancient Jemez Wui, we've learned that Wui can coexist with many high-frequency, very small fires, something that might actually work well in the patchwork of land ownership and responsibility in the Wui. But this primarily works if we regularly harvest small diameter trees and remove them from the landscape. For Jemez folks, they harvested those to heat their homes. Maybe we can support similar uses in rural communities that still use wood to heat their homes to help do two goods at the same time, supporting impoverished communities in their fuel and energy needs and removing some of the trees that are necessary to get these back to a state where they can burn in healthy ways. Firewise communities work. At Jemez, these persisted for centuries, and it is a remarkably similar model to the one that we use today. This is not theoretical, this is not in the abstract that it works in some modeling scenario. This worked for Hamish people for 500 plus years. Finally, we need to move away from the Smokey Bear meme, which emphasizes a world without fire, and need to develop our own cultural values for what fire can positively do for us. It's going to be hard. I can't claim to have answers for this, other than to say that Paul Tosa and other Hamish folks convinced me that it's possible, but we need to find that for ourselves. Although Hamish people and other indigenous societies can't prescribe how we live with fire today in our modern economic, social, and technological contexts, they can very clearly illustrate what's possible, and often in mechanisms that have analogies today, despite those economic and technological differences. So while we cannot go back to the past, we can learn from it for a better future. And with that, I thank you for your patience. And I want to thank my many collaborators, especially folks at the Pueblo of Jemez. And if you're interested in reading about any of these, this is all nestled in these three papers here. Thank you very much.
Thank you, Chris.
Hello, everyone. Thank you very much. My name is Michelle Newcomer. I'm a research scientist at Lawrence Berkeley National Lab, And today I'm going to be talking to you about my wildfire work, specifically addressing impacts and wildfire management strategies. I would like to acknowledge all my collaborators on this project. This is not one project I'll be talking about today, but multiple projects across many different fires in California and the Western US. And so there's many folks here, even some here in the room today, who have helped make this work possible. Fire regimes across the Western US have changed dramatically over the past few decades. In prehistoric California, for example, wildfires burned upwards of 4.5 million acres. And so species like the California giant sequoia and the California blue oak, they are incredibly resilient. They're adapted to fire, and they're reliant on these low severity frequent fires. Now, this most recent upward trend in wildfires that we see today is driven largely by unprecedented megafires that are pushing our fire-adapted biomes beyond their capacity to withstand change. So under future climate change conditions, we expect, and much research does suggest, that mega wildfires will increase in the Western US. At the landscape and watershed scales, fire plays a critical and unknown role on biogeochemical cycling, water partitioning, and resulting water quality. For example, fire has a very complex and varied impact on nitrogen and carbon cycling, and this depends entirely on the prior fire history and the climate conditions of a region. So while much research does exist about the growing impact of fire on water supply, our ability to predict these changes to the water cycle are limited because of feedbacks in nonlinear processes in the soil across the surface water and groundwater continuum. Much research also exists that supports the idea that fire is a fundamental ecological process that supports the coevolution of hydrobiogeochemical processes and water, and that the coevolution of these variables in response to wildfire is a process that remains poorly understood. So while acknowledgement of the importance of wildfire research is at the forefront of our collective agreement these days, few programs and funding opportunities exist to support wildfire research outside of the scope of human health. So current wildfire sampling frameworks, they're narrow, they're focused on immediate decision support based on human health and emergency response. Water quality is the perfect example of this. So while these efforts are critically important, they actually miss a very important opportunity to use science, a science-guided approach to decision-making. So a framework is needed that allows for this unprecedented community collaboration to collectively assess responses in a watershed from genome to watershed scales, and with a level of readiness needed to rapidly respond and evaluate these events to improve the predictability. So as part of a CAL FIRE Forest Health Research grant I obtained in 2019, my goal with this project was to establish guidance and best practices and the necessary framework for wildfire research to support decision-making. So the necessary steps of this framework include establishing wildfire as a next-generation research topic, developing interdisciplinary rapid response guidelines and protocols, and lessons learned from implementation activities, and these include on-the-ground efforts. Also identifying funding targets that center on wildfire. This is important for agencies to consider when creating funding opportunities, as well as designing field sites with wildfire central to the design. And finally, advancing new tools, protocols, and guidelines for our predictive understanding. So establishing wildfire as a next-generation research topic can be synergistic across the human health and the watershed health space. So here I show lots of the types of research questions that are possible. I'm not going to go over all of these, but many of the research questions across these two spaces are actually quite similar. So with proper foresight and planning, wildfire research questions designed around decision-making can also effectively contribute to scientific knowledge. A missing component here to making this type of research a reality is a set of rapid response guidelines and protocols that really outline the short-term and the long-term responses across surface water, groundwater continuum. So our research that you will hear about today, it points to the importance of understanding the role of land management, so prescribed fire, thinning, crown burning, these types of fires to help maintain forest and water health. So despite what we know so far about the role of land management for maintaining water and forest health and water quality, there is a great need for research to improve this understanding of how to utilize fire management as a strategy to promote resilient systems. So today I'm going to go over a few case studies, and so you'll hear about some successes as well as some failures of partnerships and lessons learned. And so these are critical to establishing wildfire research as a mechanism for supporting decision-making. So these are the 4 examples I'm going to talk about today. They include many components that I discussed previously, including a rapid response science component, as well as a science for guiding decision-making. So my own expertise, it relates to water quality and water quantity services that are critical for California's water strategy. In 2017, the Tubbs and Nuns fire occurred in Sonoma and Napa counties. I was already working with Sonoma Fire, and that same day that that fire occurred, we mobilized very quickly with our collaborators at the USGS and Sonoma Water to immediately respond to the fires. So we worked to launch the first watershed-scale rapid response investigation of wildfire impacts on water and water quality. This work specifically addresses the research question of how back-to-back fire years, compounded with drought, will impact future water supply and water quality. Our rapid response strategy allowed us to quickly pivot all of our other measurement and modeling capabilities to explore the vulnerability as well as the potential resilience of this watershed to fire. So you can read more about the work at the link on the bottom of the slide there. So we have 2 broad research questions for Sonoma Water that effectively bridges the human health and the watershed science space. We focused our efforts on groundwater surface water interactions because of the pressing need to sustainably manage drinking water in California. So groundwater is often ignored in this context, even though fire changes runoff characteristics. This allows for deep infiltration into groundwater and potentially contaminated water deep into the subsurface. This is also an environmental justice concern since the most vulnerable communities often use groundwater as their main drinking water source. So in this watershed, where 30% of the watershed has burned since 2017, we are finding little evidence of acute and persistent changes in river chemistry, including nitrate, sulfate, metals like iron, manganese, mercury. All of these things are harmful to human health. The water quality and the hydrological conditions have returned to baseline conditions despite new fires occurring each year. So this was surprising to us. And what we're asking right now is, how can our research help us understand this apparent resilience and understand why this watershed is responding differently and responding quite well to wildfires, where many fires in other watersheds are actually producing major water quality and hydrological changes. And this also brings up the important point that in many fire-adapted ecosystems, fire can be good for forest and watershed health, and this may be a good example of that. So the next year, in 2018, the devastating Camp Fire occurred in Paradise, California. So I'll share some lessons learned from this experience. I worked with the Paradise Irrigation District, and we conceptualized what a rapid response surface water groundwater monitoring campaign would look like. And this was about a month after that wildfire. And so despite our best efforts and the incredible urgency of the water agency, we unfortunately could not launch this program. And the reason is that resources do not exist to support this type of convergent human watershed health rapid response effort. Disparate funding resources, including just little bits here and there to scientists makes it very difficult for any type of science to inform decision-making. So here in this example, there were different analysis methods, little sharing of knowledge, little leadership on the topic. This really highlights the consequences of the lack of foresight. And the consequence is that there's a lack of scientific rigor for sound decision-making and introduces potentially huge blind spots and future vulnerabilities. I highlight another example here of the 2021 Caldor fire in California. My colleagues Erica Cirilla Woodburn, Jackie Pena, and myself developed and launched a post-wildfire water chemistry and erosion observational campaign. And we wanted to assess how the watershed will respond to the Caldor fire. This was actually quite a fortuitous example of a watershed where research investments were already placed in this watershed. There was already funding to investigate a hypothetical wildfire in this watershed using a hydrological model. So Erica and her team, they developed this hydrological model in previous years to understand how the watershed may respond to a hypothetical wildfire. This helped establish baseline conditions as well as baseline research that was critical to our success after the Caldor fire occurred. So we quickly mobilized prior to the first rain events of the fall to obtain water, ash, and soil samples and installed erosion pins along 2 hillside transects of differing burn intensity. And our goal was to measure sediment movement through time. The success of this effort was made possible by our partnership with a local nonprofit group called the American River Conservancy. And we implemented this water quality sampling program across 21 spatially distributed sites. And these sites already had 7 years of baseline data collected by this nonprofit group with the help of a citizen science team. And so we sampled for the chemical characteristics and have already conducted numerous additional sampling campaigns with the citizen science team. About 11 spatially distributed field campaigns have happened since September. And so these efforts also highlight the critical role of partner organizations and pre-fire investments in making this type of convergent human and watershed health science possible. So in this next example, I highlight the work of my colleague Ricardo Gonzalez Pinzon and their rapid response efforts to address the Hermit's Creek Peak Calf Canyon fire in New Mexico, which was actually occurred relatively recently, just about 2 months ago. So within days of the fire, Ricardo and his colleagues, they responded quickly, and their sampling efforts include deploying sensors in the river, and they deployed those quickly after the first signs of fire. And they also did this at many other time points throughout the burn period. I would like to also highlight that their prior work on a different fire is published in Nature Communications, that's shown at the bottom left there. And so from a science context of this fire, the Calf Canyon fire is now the largest in New Mexico's recorded history and started out as 2 controlled prescribed burns. This has prompted a halt of all prescribed burns in the state. So this fire also has the potential to impact downstream drinking water resources. This example here highlights that a set of opportunities exists between state and researchers to coordinate land management activities, such as prescribed burns, and science activities to address the pressing science challenges associated with wildfire and water quality. So from all of these different case studies I've shown you here, one thing in common is that our science has the potential to drive the decision-making process at the local level. At Sonoma Water, for example, where our partnership was critical to that success, this includes novel science approaches, at watershed scales, novel sampling techniques, as well as new ways of thinking about the watershed, from omics to water to chemical characterization, pre and post fire. And so I emphasize the importance of that baseline data. And so despite Sonoma having all of this available for resources, other watersheds don't have these type of resources. State and local agencies need guidance and scientific expertise and protocols to address these science challenges. So our collective fire community has spent a lot of time identifying the most pressing research investments where scientific breakthroughs are needed, and I will talk about these very briefly. So in 2021, we wrote a white paper to Department of Energy calling out the need to engineer a fire community observatory. And this is built on a foundation of domain scientists across disciplines to guide and implement methods to optimize a rapid response monitoring framework. And this would include monitoring before, during, and after fires. We issued many recommendations in that white paper, which you will see on the next slide. So if you're interested in a copy of this, please do reach out to me. So here is a quick glimpse of some of that collective brain power from our community. We've identified many new large initiatives and investments that span the timeline of pre- and post-fire investments, things such as groundwater characterization, new prediction tools, and then post-fire investments such as rapid response teams. Some of our recommendations include new initiatives for breakthroughs in modeling and observational efforts, and efforts to support that synergistic decision-making. Also, reliance on land management activities. This is an opportunity for scientific investigation to co-occur with these activities. So finally, a few needed next steps from the human and the watershed health perspective. They include predicting how watershed disturbances affect watershed function and water chemistry, developing water chemistry as a very powerful indicator and benchmarking data set, and researching what confers resilience and vulnerability across ecoregions. And finally, assessing how these coupled systems evolve and rebound after fires. And we specifically highlight here that any type of response to these wildfires will have to be quick and will have to include some level of baseline pre-fire investments. So a commonality across all of our projects here is that we are actively informing stakeholders and policymakers on our management practices to mitigate wildfire impacts. We've partnered with federal, state, and local agencies to conduct this research based on needs. And a few of the activities that I have done include a briefing to congressional staffers and energy utilities, a DOE podcast on the future of water and wildfire, and a briefing to California state senators and legislative staffers on wildfire impacts. So with that, I would like to thank you for your time today and encourage you to please reach out to me for questions, and I'd like to acknowledge all my collaborators shown here. Thank you very much.
Thanks, Michelle.
Hi, everyone. My name is Sander Veraverbeke, and I lead the Climate and Ecosystem Change Research Group at VU Amsterdam. I want to thank the organizers of this session for having me here. And I will talk today about climate fire feedbacks in the high north, in the high latitudes. And I'll start as soon as my first slide pops up here. I'll make use of the time to already thank all my collaborators, PhD students and postdocs, external collaborators for their input set as well. All right, we're good to go. Sorry for the slight delay. I really love satellite data, and starting here with a satellite image that was taken by the VIR sensor over northeast Siberia in June 2020. And it pictures a lot of what I will be talking about. So you see in June here that the sea ice in the Arctic Ocean is still kind of breaking up. And a little bit south of that, you see the smoke and the active fires raging. And this is very far north, so this is well within the Arctic Circle. These are Larix forests that are burning, as well as some tundra fires. I'll come back to some of these Siberian fire extremes in a little bit. So I mentioned most of this here. And today I will touch upon 4 topics. First, a global fire cause attribution that we developed. Then I will continue with lightning fires in the Arctic, to then switch to some of these recent Siberian fire extremes of the last few years. And I'll finalize with some carbon feedbacks from these fires to the climate system. So this is a map that I think is well known by pyrogeographers. It shows the fire frequency on Earth. With the reddish colors means like almost annual fires, such as in African savannas, and the more bluish colors means that there is a fire every few decades or even centuries. There's a lot I could say about this map, but I will keep it short. Just that if you have a fire in California or in Arizona or in Siberia or in an African savanna, there's always a different story. There's always different drivers. And one kind of defining characteristic of a fire regime is the cause of an ignition. So I developed with colleagues this kind of first global fire cause attribution map. And some patterns, like geographic patterns, immediately appear. Is that you see that the more yellowish colors mean lightning-dominated fire regimes. Those are very prevalent in the high latitudes, not only in the high latitudes, also in remote mountainous areas in the mid latitudes, as for example in the American West, we have lightning-dominated fire regimes. And basically anywhere where people are abundantly present in the landscape, such as in the Southeast US or Europe or India or African savannas, contemporary fire regimes are dominated by human ignition. So here the bluish colors. So just very shortly how we developed this without going into the details, but we implemented a machine learning model, which was calibrated and validated with reference data from 7 different world regions. And this map explains 40 to 47% of the spatial variability in fire cause. And so if we overlay our global fire cause map with other geospatial layers, and I want to see if I have, I don't really have a pointer here, but so I'll describe the graph. So we should focus on the left column of the graph, which is the extratropical forest. So that's mostly the forests in the mid and high latitudes on Earth. So we know that these are dominated by lightning fires. About 80% of the burn area in these forests stems from lightning. We also know that these fires are burning into carbon-rich fuels, which is mostly stored in the organic soils. And on top of that, we know that depending on which model we use, we have different outcomes, but we predict more lightning in the extratropical forest, which is different than other regions on Earth. This kind of tells us that these carbon-rich extratropical forests are increasingly at risk of lightning fires. In addition, our global fire cause map could be very useful to implement in global fire models to distinguish in future trajectories between anthropogenic and lightning fires. So I'll continue now with lightning fires, and specifically then in the Arctic. And when I started looking into this topic, we can already see increases in lightning ignitions in the data records. So here for Alaska, in the last couple of decades, we see an increase in the number of lightning ignitions. This graph ends in 2015. However, actually what is happening now in Alaska, there are many lightning strikes that started lightning fires for the moment in this season And the peak of this season will maybe not be as high as the one in 2015, but it will definitely be above average. So this is currently going on as well. So maybe time to update my graph here. So we also looked, and this is with colleagues from UC Irvine, into how much more lightning we can expect because of climate change in the future in the Arctic. For that, we used observational lightning data, which we coupled with meteorological data that are good proxies for lightning, such as CAPE, convective available potential energy, and then we extrapolated that relationship into the future. And you see on the map here that we see orange and red colors, which means like a doubling to tripling of the amount of lightning by end of century if we use a high emission scenario, which luckily we're a bit below that track record for the moment. So if we look then at the graphs at the right, this is kind of plotting the same data, but along a tree line transect going from 800 kilometers south of the tree line into the northern tree line and then into the tundra. And the red line on the top graph shows us the current amount of lightning. And the blue line tells us how much more lightning we expect in the future with this uncertainty range from different climate models. And then looking at the bottom graph, if we move into a lightning-rich Arctic, this kind of suggests that fires will follow the lightning, and the fires, the burned area in the current time is the orange line. And if that will be pushed further north, this suggests that that will eat into some of that carbon that is abundantly available in these landscapes there by direct combustion, and also by kind of longer term impacts that may be the result of fire-induced permafrost degradation. We know that in these permafrost soils, these contain about 2 atmospheres worth of carbon, and fire will not release all of that, but could definitely release some parts of it. So with one of my PhD students, Thomas, I also looked in, so there are literally thousands of lightning strikes every summer in the Arctic, and only a few, like a few tens or hundreds, really start a fire. So we were interested to know, why do some lightning strikes start fires and the majority does not? We hypothesized that that may have to do with the lightning characteristics, such as the amplitude or the polarity, or landscape characteristics such as topography and vegetation, and the fire weather at the moment of the lightning strike. We found that the fire weather, so dry lightning, is really the most important predictor of lightning ignition. This may not be that surprising, but we were a little bit surprised that these other factors seem to matter so little. But that means then that we expect an increase in lightning in the Arctic, about 20% per degree warming in Alaska, for example, as there in the graph. But not only that, we also expect a higher lightning ignition efficiency, so more ignitions for the same amount of lightning. That means that those two increases will reinforce each other, leading to even more lightning ignitions in the Arctic, so up to 40% more, for example, here in the case of Alaska. Here we see this on a map, again using the RCP 8.5 scenario, and the blue colors here mean like 1 fire per 10,000 lightning strikes, and the reddish colors mean like 1 fire per 10,000 per 1,000 lightning strikes. And you see that throughout time, Alaska colors more reddish, and that red color also starts increasing in tundra areas in the far north, such as on the north slope. So that means that these tundra regions will also become more sensitive to lightning ignition. This brings me to the Siberian fire extremes of 2019, 2020, and 2021. So when this happened in 2019, I was already astonished. People asked me, like, how frequent do you have such a big fire year? And then it was followed by two more record years. So the map here that I show is a temperature anomaly map from the NASA Earth Observatory. And if you look well at that map, then you will see a clear pattern appear between an alternation of hot and dry red colors that are alternated with kind of bluish colors, which show a below average temperature in that moment in June 2021. And this alternating pattern in the mid-latitudes kind of tells us that this may have something to do with the blocking or stalling of the jet stream, which for a longer amount of time then allows certain weather patterns to dominate in a certain region. And if that means kind of warmer, drier air from the south into the same region, such as eastern Siberia, that means that you have a heat wave and drought for a longer amount of time in eastern Siberia, as was the case during these events. So here in this graph, you see the cumulative number of fire pixels detected by the MODIS satellites throughout the fire seasons in eastern Siberia. We have data since 2001. And within that relatively short record, we find that those 3 last years were the record years. And I'm kind of happy to say that 2022 will not break these records. So there is quite a bit of fire activity in Alaska, but not so much in Siberia for the moment. But still, we kind of really want to understand what was going on in eastern Siberia during these last few years. And so with my PhD student, Rebecca, we looked at what the dominating weather patterns were during these extreme fire events. And so when we plot the temperature anomalies and also the vapor pressure deficit anomalies at the moment of these fire anomalies, then with a little bit of goodwill, you can see the same alternator pattern between hot and dry areas and kind of the colder regions in between, which is the same as in these slides a few slides ago. So this really tells us that this is related to the atmospheric blocking events that bring hot and dry weather for a longer amount of time into eastern Siberia. So Rebecca found that this blocking of the jet stream is not the only kind of climatic cause of these extreme fire seasons. If you look at the graphs here, then on the y-axis you have what we call the correlation with the Arctic front jet. So basically high correlation means we have an atmospheric blocking event, a low or negative correlation means we don't have that. And we see that there are also weeks in which we have a relatively high correlation with the Arctic front jet, but not extreme fires. However, if we take another variable, it's the timing of the snow melt in spring, in combination with this atmospheric blocking, then we see that all these extreme fire years happened when there was an early snow melt, so in early spring, that then a few weeks later was followed by one of these blocking events of the jet stream. And that is true for forest fires, the graph on the left, but that's also true for fires farther north, the tundra fires. So on the graph on the left here, we show that there is a kind of latitudinal gradient in which these two driving variables have a different importance. The early snowmelt has a more negative, so more influential contribution further north, and the atmospheric blocking is more dominant between 500 and 1,000 kilometers south of the tree line. That's still within the boreal forest. And then if you look, the graphs on the right, to how have these meteorological drivers changed throughout time in the last few decades, we see in the blue graph that the snowmelt has become 6.8 days earlier over the last 40 years, and that the atmospheric blocking events have tripled in frequency over the last 40 years. So those two meteorological drivers can be directly linked to climate change, and if those trends will continue in the future, that will mean that we will see even more fire in eastern Siberia. This is a little video, but I don't know if I can start that without access. Is that possible to? Yeah. So, and the legacy of these extreme fire years extends beyond the traditional fire season. What we see here is smoke coming up from burnt peatlands, but in winter they're covered by snow. And you would think that these fires are extinguished, but we discovered that this is not always the case. So these are these overwintering zombie fires. So what exactly are overwintering fires? And you can kind of see this in this Sentinel-2 satellite time series. So we have on the left a satellite image from the end of the fire season in 2019, where you see the burn scar, and it looks like the fire has extinguished. It's not actively spreading anymore. Then you see the same fire scar covered by snow in early spring. And then surprisingly, so this overwintering fire is kind of invisible to the satellite, is smoldering underneath the snow in these peatlands. And then when fire weather becomes favorable again, this overwintering fire kind of transitions from a smoldering phase to a flaming phase and can start spreading again. And that's what you see in the third image. And then it can kind of burn additional area and so kind of contribute to the next fire season, kind of extend that legacy there. So with my PhD student Wang Shan, we were kind of interested in like, okay, but how important is this phenomenon? It's a very intriguing phenomenon. Does it also happen a lot or not? Well, most of the fires in eastern Siberia are caused either by people or by lightning. But so we found that these overwintering fires are maybe more widespread than we first thought. It's a rarity, but still, we found that in almost a decade of data that they account for 3.2% of the burned area. In the large fire year of 2020, that was 7.5% though. And we can kind of see these overwintering fires as an emerging characteristic of a changing Arctic fire regime. This brings me, last few minutes, I can still spend on the carbon feedbacks, and we see on the left here a map which maps fire intensity measured from space. We see high intensity fires in boreal North America, lower intensity fires in Siberia, which has to do with different dominant tree species. I'm kind of go in detail about that. We are also interested to know like how much carbon do these fires actually combust, and thanks to many campaigns, including NASA above, we have several hundreds of measurements in Alaska and Canada. We know that these fires combust quite a bit of carbon. That's like between 3 and 4 kilogram carbon per square meter, and that's a lot. It's like only tropical peatland fires that can combust as much or more than those fires. But in Siberia, basically, there were almost no measurements of that. And in 2019, I was lucky to venture out to Siberia. And these times, I really have to say that I was lucky then in 2019. We measured burn plots there in 41 larynx burns. And we found that like the combustion was also around 3.3 kilogram carbon per square meter. The majority comes from these organic soils. So it's the trees contribute like up to 10 to 30% of the carbon, but most of the carbon that is emitted is from the organic soils. So we measured in these different ecosystems. We had some more mature open forests with larch and also pine. We had some younger, denser stands, earlier succession larynx. That's that. We also found that the amount of carbon that is combusted is a product of how much fuel there is available. So if there is more fuel in your ecosystem, that will on average lead to higher combustion. That's maybe somewhat logical. And that is combined with the fire weather influence. So if it's drier and hotter wet conditions, then the combustion completeness will be higher as well. Those are the direct kind of combustion impacts from those fires, which is relatively high compared to other fires on Earth. Now with my research group, I'm very interested in the question is like what happens on a longer term perspective with these ecosystems, which are permafrost landscapes. So what happens with the permafrost after a fire? Does it just recover after a fire, or does it degrade? And if it does degrade, is that more gradual or more abrupt? And how much additional carbon emissions can come from that abrupt permafrost thaw? I have some very preliminary data here in which we see that the blue box plot has a deeper active layer, deeper thaw depth in summer than the reddish unburned control plot, so that's several tens of centimeters deeper. We also found that land surface temperature from Landsat is a very good proxy to kind of map this post-fire tau depth over different fire scars, which may enable us to kind of scale this up over a larger region to improve our mechanistic understanding of these processes. And then to summarize, so extratropical forests are increasingly at risk of lightning fires. We expect more fires in the Arctic because of compound increases in lightning and dry fuels. The Siberian fire extremes were driven by compound early snowmelt and atmospheric blocking events. And these fires in the Arctic have strong carbon and climate feedbacks because of their high combustion levels and because of the potential impact on permafrost. So with that, I would like to thank you for listening, and also the Dutch and European Research Councils for supporting my research. Thank you. Happy to take questions afterwards.
We're moving from the Arctic to much more pleasant weather.
Aloha, everyone. My name is Alyssa. I'm a postdoctoral researcher at the University of Hawaii at Manoa. I have a question for the audience. Can you raise your hand if you flew into Hawaii for the conference? Okay, and then my next question is, can you raise your hand if you've heard Hawaiian language spoken, other than the airport? Okay, thanks. Thank you. Okay, so I'll be presenting on wildfire under a changing climate in the Hawaiian Islands, but this work is an ongoing collaboration between many groups and people. Now, there are two main takeaways I hope to convey during this presentation, and the first is that wildfire is a significant issue in the Hawaiian Islands. And the second is that historic Hawaiian language materials are extremely valuable resources for addressing themes in earth sciences, and for this session in particular, a way to view geology through a cultural lens. So wildfire is not typically associated with the Hawaiian Islands, but it's actually a significant issue that affects ridge to reef health, threatening forests, coral reefs, biodiversity, human communities, as well as natural and cultural resources. Fire is not endemic to the Hawaiian Islands or Pacific Islands in general, and most of the fires in Hawaii occur in dry, non-native invasive grasslands that make up 25% of Hawaii's total land area. And the majority of these fires are human-caused. This chart on the bottom shows here that the percentage of land area burned in Hawaii is actually equal to and sometimes even greater than areas burned in the continental United States, including in just the Western United States. So I'll show here now some news headlines from the past few years on fires that we've had. So in 2018, there were large wildfires that burned through the west side of this island, Oahu. So when you see pictures like this, it's seemingly out of place for somewhere when you think of Hawaii. And then we saw this again the next year in 2019 on Maui, and ultimately over 20,000 acres burned in a single summer, and that continued on to the next year, when in 2020, fire burned about 1/3 of the island Kaho'olawe. And then in the summer of 2021, there was a huge fire that burned 40,000 acres on Hawaii Island. This fire was all over the news, and it's one of the largest wildfires in recorded history for the Hawaiian Islands. So all of these newspaper examples are given to show that wildfire is a prevalent feature in Hawaii landscapes. So here's just a little bit of fire science as a way to sort of take a closer look and explain, so what's going on here? Now, fire regimes, like we heard about in these previous talks, are these longer-term patterns of fire. This refers to climate, how climate, ignitions, vegetation, how all of these factors interact to drive patterns that we see over time that affect landscape scale. So fire regimes in Hawaii have been altered from infrequent wildfire occurrence to greatly increased frequency, intensity, and size over the last 100 years. So if we look at ignitions, before human arrival, ignitions of wildfires included volcanic activity or infrequent lightning strikes on land. But since human arrival, ignitions are almost entirely driven by people. So another key driver of this change is the change in vegetation, particularly the expansion of these non-native invasive grasses. And then finally, we have climatic processes occurring. So these are patterns of wet and dry seasons in Hawaii and longer-term El Nino cycles driving Pacific droughts. So here's a plot of Hawaii wildfire occurrence over time, and we can see that as we come into these more recent decades, the area of land burned by fire is growing larger and larger. And what that indicates to us is that it's important to think of this problem as something beyond fire suppression, because all of these fires, we won't be able to put them out, but we really need to think about what's causing the fires in the first place and what was going on before that led to this point. So how can we look into the past to help inform the future? So one way to better understand wildfires in Hawaii's history is looking into the archive of historic Hawaiian language newspapers. So the headlines that I just showed at the beginning of this talk were from contemporary newspapers in the past few years, but there's actually a rich history of literacy in the Hawaiian Kingdom and Hawaii Territory days as well. So from 1834 to 1948, over 125,000 pages of Hawaiian language print were published in more than 100 newspapers, making it the largest archive of indigenous language writing in the Western Hemisphere. And these newspapers were not like the newspapers we have today, but they were really embraced as repositories of knowledge and history. And in some of these articles, Native Hawaiians documented natural processes that they observed locally, including fires and fire impacts in Hawaii, and outside of Hawaii as well. So this extensive repository provides years of discussion and change that is not included in the current dialogue. The history and the books that are written about Hawaii have been written without the Hawaiian voice, so it's really an incomplete picture. And while this repository has now recently become digitally accessible, the entire archive is in the Hawaiian language, and there are less than 2% of people in Hawaii with some fluency in Hawaiian needed to fully utilize the resource. So there are excellent groups doing work on this topic, and some scientific research has been conducted utilizing this resource. For example, here, this is an example of identifying a major hurricane that struck the islands based on historical accounts from the newspapers. So now, learning from all of this, we aim to build a more complete Hawaii wildfire history from the Hawaiian perspective. So to guide this project, we developed a set of research questions to investigate, specifically what were Hawaii wildfire contexts in mid-19th to 20th century, what were the human responses and the social perceptions of these fires, the ecosystem impacts, and then finally thinking about how might these historical changes be contextualized to contemporary themes in fire science today. So I'm going to give here a quick overview on the research methodology, which is adapted from the university. So to search the newspaper archives, I use an online Papakilo database. And the first step is to choose indicator words on the topic to search for. So in this case, if I want to search for fire, I'll type in the word for fire in Hawaiian, which is ahi. And you can see that gives about 45,000 results. So you can add indicator words to narrow the search or narrow the search down by years. But keep in mind that this is entirely in Hawaiian, so you can't just type in like ecological impacts of wildfire on Hawaiian Islands. You have to really think about how these concepts would have been expressed in Hawaiian during that time period. So from there, the mentions of the search terms are identified. Here's what an article might look like. And then the findings are filtered to ensure that the content is relevant. So as you might imagine, there are a number of challenges with working with this material. Sometimes the text is automatically generated. Here's an example using optical character recognition software. So it could look like this, and you really need to go back to the original document and transcribe it to make sure that the content is correct. So hopefully this gives a brief overview of what a task this is. So to further narrow down searches for articles about fire, for this project, we used the extended multivariate Enso index shown here. So essentially what this is, we use this to identify periods when it was hotter and drier, when fires may have been more likely to occur. So all this plot shows is these negative values representing cold Enso phases, and in blue, and then while positive red values represent warm phase or El Nino events. So I'll share here now some preliminary findings from 3 case studies, all of which occurred during strong El Nino years. So each case study is a wildfire event that was documented in the Hawaiian newspapers, and these occurred on different islands and across different decades to sort of give a span of time. So we'll go back first to 1877 on the island of Kauai. And articles here described a large fire that was started by people branding cattle in the mountains. And this fire spread across sugar company land, and it burned in the mountains of Kapa'a. And this group called Hui Kauaiho wrote in the papers describing the fire spreading across hills and valleys and how they all joined together like warriors to fight this fire. And they worried about people residing in those areas, in these places, and they described, it was interesting, they described the way that the fire looked like a lava flow on a cliff. Another interesting thing to note is there's a map of Kauai, and Kauai is a very wet island, and this fire occurred on the windward side of the island, so that's the rainy side of the island. So it's interesting to think that this large fire occurred even on a very wet island on the wet side of the island. So next, over 20 years later, in 1901, there was a huge fire on Hawaii Island that burned 30,000 acres and lasted 3 months until rains ultimately extinguished it. So this fire was started on sugar plantation land, but it also burned into pasture land and native forests as well. So here, this quote from the Hawaiian newspaper, Ke Aloha Aina, reads, "Aia ke kahiahi nui ke ulupa'ala ina malako a me na ulula a hamakua. A ua ho'oi loa I aku I kia mo lama muli o kai kaiko kamakani a me ka haule ua ola aia no ua ahine ke aala." There is a large fire destroying the sugarcane fields and forests of Hamakua, and it was intensified recently because of the strength of the wind and the lack of the rain. So this highlights that the knowledge and awareness of fire conditions and the resources that people worried about then are the same things that we're worried about today. It's also important to note here that this fire is the large fire that prompted annual reporting of area burned in Hawaii. So this, our last one, 30 years later, 150 acres of Haleakala ranch land burned on the island of Maui. And this article describes how over 200 people joined together to put out this fire. They were really worried about people's homes and land being damaged. One of the articles notes how dry it was, not just on Maui, but on other islands as well, and the lack of rain for some months beforehand. So looking back again at the story of changing fire regimes in Hawaii, we see that large fires today are not unprecedented, and they're not only restricted to those dry grassland areas, but they can burn native forests as well. So fires have been ignited by human activity, burning on plantation and ranch land, which these landscapes are also controlled by humans, and their impact to ecosystems, water, soil, and people. And what's really interesting for Hawaii is that the big driver of wildfire today is actually the decline in agriculture combined with all the non-native invasive weeds that are adapted to fire. So the biggest correlation with that beginning plot of the increase in fire in more recent years is this huge decline in agriculture since around the 1960s. So here's a chart of one example, sugarcane production in Hawaii, and you can see this dramatic decline in the more recent decades. So these abandoned agricultural lands are not being farmed anymore, and they're essentially dominated by non-native grasses accumulating fuels. And then also, there are no longer these large groups of people working those plantation lands like before, like described in the newspapers, where they could drop everything and rush to tend to the fire and have knowledge about that place and the resources that were available. So how is this all placed in a contemporary context? And what are some solutions? So there's been a national effort to bring these pieces together called the Cohesive Strategy for Wildland Fire Management, but Hawaii is a unique tropical setting where fire does not serve an ecological function. So it's really important to make these efforts locally relevant to create fire-resilient landscapes and fire-adapted communities, because it's really the people in these communities that have the knowledge about the resources and the capacity to intervene. So for Hawaii, fire-resilient landscapes mean things like reforestation efforts, strategic fire breaks, vegetation and roadside management, as well as education and outreach, and community wildfire protection plans. So from the Hawaiian newspapers, we see that these issues are quite similar, and they were warning about this from even back then. So I'll conclude with the two main takeaways from the very beginning, that wildfire is a significant issue in the Hawaiian Islands, and that the Hawaiian newspaper repository is an invaluable resource of Hawaiian perspectives that have largely been left out of the conversation, but they provide important contexts and a more complete history for addressing earth science issues of today. Mahalo nui. Thank you for listening.
I'd like to thank all the speakers, and now we have time for people here and on Zoom to ask questions. While we get organized, please use the microphones to do that, so it will be captured in the Zoom. And while we're doing that, I have a question to start this. I guess fires have been around on Earth forever, and they'll probably continue to occur. And they have different triggers, they have positive roles in ecosystems, they can cause negative effects. And now that Earth has so many people in it, we need to manage fires. From your perspectives that come from your experience from different locations, if there was one thing you would suggest for people who want to manage fires or live with fires or take advantage or do something with the fires, what would that be? And we can just go, there's a microphone here, and feel free to use it.
I'll start, sure. Maybe I'll take this out. We can pass it around. It's a great question, and my answer may not be particularly surprising given my perspective, but I think that it's probably really essential that we do whatever we can to learn from long histories of experience of place-based peoples, especially indigenous peoples, that both the hubris and ethnocentrism that comes with being a part of the modern world shouldn't be impediments to humility and learning from other cultural experiences.
Chris.
Yeah, a great question. I think if in my presentation I had the map where we show the difference between lightning and anthropogenic fires, and the huge majority of fires on Earth are started by people. So people have a huge influence on fire regimes, both as an ignition source by fragmenting landscape, changing the land use, clearing the ecosystems, also by suppressing. So that means that we have a lot of control that we can also use to kind of coexist with fire, because we're not going to be able to stop every single fire. And we live in an unprecedented era that we have an upward pressure of climate change. And that, I think, is something that is globally consistent, although there are differences in some areas. That's even more profound. But so I think it's important that we kind of mitigate the negative impacts of fire, and also do not see fire as only something problematic. That's sometimes how it is depicted in the media, but there are a lot of positive roles, and we saw some of that in the presentations of fires, that both the cultural heritage and also the biodiversity that it can bring to ecosystems.
I think this question is really important because it raises another question of what do we want our landscapes to do for us in terms of resiliency, and what does resiliency mean in a landscape for things that we care about, like water and ecosystem services. In my experience in the Russian River watershed in California, for example, as I mentioned in my talk, our findings were quite surprising to us at first, but then not surprising when you look at the context of this Mediterranean watershed with a very long history of fires over thousands of years, as well as cultural burning. So I think there's a lot to learn from the cultural history in terms of how the landscape has been maintained over thousands of years, but also we need more research to really understand how to manage it given the constraints of today, given human impacts, and given how we rely on the landscape and what we need the landscape to provide for us. So I think there's multiple factors here that I think it's important for research to consider both the social side as well as the scientific side, for really asking, what is it that we're trying to find out? What is it we're trying to understand from the landscape? If you think about what steady state means, I think that's a research question right there, since landscapes evolve and new vegetation emerges and new land uses emerges. So I think from a land management perspective, I think there's a lot more that we have to do to learn how to manage these landscapes, given today's context.
Yes, I agree with all that. And I'll just add an example from Hawaii and about how humans have control or can affect the landscape. So when there were some pretty big fires burning through the landscape, the only place that was saved was a golf course. So that sort of shows that, humans and what they do with the land can affect what happens and where the priorities are.
That's interesting. I think we have questions from the Zoom.
Yeah, we have a question from the chat. We heard about human fire suppression leading to large, intense fires in New Mexico. Is that a significant factor in the Arctic fires as well? Also, what, if any, are the implications of increasing Arctic fires for reindeer herds that are already under pressure from many different factors?
So what was the exact first part of the question? I understood the impact on the reindeer herds, but the first part I didn't fully get.
Yeah, the first part is about if human fire suppression, like we heard about in New Mexico, is leading to these large, intense fires, if that's a significant factor in the Arctic fires as well.
Yeah, so in boreal landscapes, the human suppression really kind of focuses around like the settlements and the towns. So it's kind of more localized because most areas are quite remote. I'm not aware that locally in these areas that has led to bigger fires. The human fires are mostly smaller in these wildland-urban interfaces, and the lightning fires are bigger, mostly because they are not extinguished and they just can keep growing in like an unfragmented landscape. So that's one. I think there are also big differences in how people use fire and start fires between Siberia and Alaska and Canada. So because I think in Siberia, people still kind of make much more use of the land in a more kind of natural way, and also use fires around the little villages more often. So that's that. And then the second question, so I do think fires create a lot of like a fragmented landscape where you have patches of different ages of forest, and yeah, that attracts sometimes different animal and also plant species. So in some degree, if yeah, a new burn scar is yeah, not good, like to provide the resources for different animal species that may have negative impacts. There can also be positive impacts then for other species. So that's a really difficult one to really account for. So I think it's important that we keep the current fire regime at its base, if that would be possible. And I mean, so we don't have to extinguish every single fire, but we also don't want to see the increases that we currently are seeing in the Arctic. But since most fires are started by lightning, it's more difficult to suppress those than the human-dominated fire regimes.
Any additional questions? Come to the microphone, please.
Thanks to all the speakers. Anthony Docedo from University of Wollongong in Australia. I have two questions, if that's okay. One is specifically for Chris. I was curious, looks like you guys in Southwestern US have much more widespread record of past fires than we do in Australia. I'm curious, how do you get past fire extent and past fire intensity?
So in our study, we looked at fire extent using the percentage of individual trees scarred in a given year. So we have for that map where I had all the white dots, those are all tree ring sites, and each one of those sites would have anywhere between usually 8 to 10 and as many as maybe 50 trees. And those would be in aggregate, treating each tree as an instrument observing fire at that spot, right? And so in fire years in which you had a large number of any of those trees that were alive to record fires, recording a fire in that year, we considered those to either be years with large amounts of fire. Whether it's individual fires, you can map that out. We did not in that particular study. And years below that threshold that recorded fires, but not in a replicated way. Those were years with small fires. And so that's how we got at extent in this study. It was very broad brush and not mapped out. If you have a kind of a well thought out sampling frame, geographic sampling frame, you can do that. You can actually map out the areas. But with ours, we didn't do that. There's a part of our team was working on that for the Jemez Mountains writ large now. That's mostly post people. The record, beyond 1600 gets really thin in most of the Jemez Mountains. So after 1600, we can map fires pretty well. But before that, it's mostly based on this percentage of individual trees that's scarred in a given year.
So relating to tree rings, right?
Yes.
Yeah, it's a bit of an issue in Australia. We don't get many trees that actually give us, such a beautiful tree ring record. It's one of my students here. She knows how painful it is to reconstruct these past fire histories. My second question is maybe for everyone on the panel. Chris was saying we can't go back to the past. We kind of have to. I don't know in North America and in Hawaii, but in Australia, we can't afford doing fire management the way Western people have done fire management in Australia for 200 years. It's just not working. It's a disaster. And you talk to First Nation communities there, they pulling their hair when they see what's going on with the environment. In Australia, there is increasingly this sort of awakening that we need to take on board. We need to work with First Nation communities to embed their knowledge and work with them to manage the environment. What is it, from what you're saying, from what I hear from before of you, it sounds like in North America, in Hawaii, this is not happening yet.
Well, so when I made that statement, I meant in a very literal sense, right? The communities that lived in the Jemez Mountains for hundreds of years were farming communities. I mean, there were more people living there for those 5-6 centuries than live in that area today. But the economy is completely different. It's mostly a recreational. There's a national recreational area in the Jemez Mountains, and so it's mostly service industry related to that. We can't go back in that. We can't establish farming communities in these places again. That's not going to happen. What's going to happen in the future is going to be new. And I think it's the same thing in Australia. It's not going to be the same. It can't be the same, but it can still learn from that past, right? It can still be informed by that past in ways that meet the modern world and the modern situation with a great deal more respect, empathy, understanding of these other sets of values and other knowledge systems that can benefit large proportions of the population and the environment. I'll let other people speak to that.
Yeah, thanks. One thing that I was kind of at least somewhat happy to see in Chris's presentation was that the current Firewise project then has some agreement with what the kind of more indigenous people did back in the past, kind of clearing and thinning the fuels. So it's not that every single aspect is like something completely different, but I mean, of course, I largely agree with you that the more knowledge you can take in from the past, the better. And I'm not an expert in the Australian ecosystems, but I do know you had some big fire years in the Southeast Australia with the eucalyptus forests. And I guess there is a lot of knowledge there that could be integrated, but I'm not an expert enough to really comment on that on these ecosystems. So I'll pass it on to the next one.
I appreciate that comment, and I will say that there's a lot of conflict that exists regarding implementation of best practices and historical knowledge, specifically because communities don't want fire, they don't want to breathe aerosols, and they don't want to see consequences of that. So it's very conflicting in terms of how do we implement the best land management practices we have versus maintaining what people want for their landscapes. And it's a very hard balance. And I think I'm very skeptical that we will be able to reach that sort of balance because of that conflict with our current population. And I think with mega wildfires that we see today, they're just of such an unprecedented size. And I think a path forward is going to take a lot more than just implementing some of these best management practices, but we're going to need something of a much larger and much more widespread scale to mitigate these impacts.
Yes, I think for Hawaii, since fire serves no ecological function, it would ideally like to go back to the past where it's all native species and not many human ignitions, although it's simply, it's a big task. And so we're sort of working with what we have and managing the fuels that exist and promoting education and outreach to manage whatever the situation is as best as possible. So we're looking to the past to inform the future, although acknowledging that it's a very different setting than it was in the past.
Can you share with us what you learned from the native people in Australia?
Well, it's just, I'm not an expert. I'm not a fire ecologist, unfortunately. But I work with some of them, and I work with indigenous communities to, studying, the effect of cultural burning on the environment. But I find that fascinating to see this North American and Hawaiian perspective on the interface between this society that is, Western dominated community and the First Nation communities, and how knowledge is transferred. I mean, from what I hear in your communities, it seems to be a long way before this First Nation knowledge is actually integrated in policy making. I'm not saying this is happening in Australia, but again, there's this awakening that we really need to work with Aboriginal communities. And it's not, and we couldn't say to them, oh, let's study the past, which is us as scientists, a lot of us, that's what we're doing. They stay here, and it's the same in North America, it's the same in Hawaii. These communities, they are still here. So we just need to, go talk to them. I mean, I'm preaching the converted here, but policymakers, which are not us, but like you said, we can inform policymaking. Policymakers need to be more active in engaging with First Nation communities.
I'll make one more comment related to that. And one of my colleagues who is not here in the audience, she's a colleague I've worked with for a long time. She works with First Nation communities. And one of the most important factors to consider is that there is no way to just implement a project. It takes many years of relationship development with these communities to be able to have those conversations and enable decision making that meets many of the challenges that we're faced with. And so I'm sad she's not here to comment on that, but I think one of the things that I push for when I speak to policymakers about this is that funding is needed, not just for the science perspective, but also for developing those relationships from the very beginning, enabling the science to happen years down the road. So it's a lot of foresight and thinking ahead of time before these projects can happen.
Yeah, thank you.
Thank you.
And thanks to Edina for organizing this session. It's marvelous to see this here.
It's all the speakers that took their time to come and share with us. And with that, I guess we'll all thank them again for being here. Oh, is there more questions? Perfect. Thank you.
Thank you so much for all the presentations. I had a really specific question that I wanted to sort of throw out there to the panel, and then I had a bit of a follow-up to this last discussion. So the specific question is about the value of smoke. And I've been sort of thinking about that. And so, do you or any of the other speakers have any ideas on that already? The cultural value of smoke from fires.
I'll make a first comment to that, in that I don't know what the exact value would be, but I know that at least from today's perspective, there's little value in smoke. But that's not to say that there isn't some value in that. And that's as far as my expertise goes on that subject.
I would, I guess, comment from a public health standpoint. My understanding from the work of some of my collaborators in Australia is that there aren't good effects of smoke on human health, full stop. But the overall health burden of smoke from low severity, cool season, planned burns is much lower than the smoke from a megafire, right? From a large, high severity event, and that some of those wind-driven events in California in particular were just really, really bad compared to what would be maybe a chronic but detrimental contribution from what many fire scientists would think of as important, good fire in many, but not all, say, Western US forests.
I'll make one more comment, and I'm thinking about this question more. I have read some literature suggesting that aerosol deposition, from wind transport, plays a role in biogeochemical cycling. So I think we can reasonably infer that there's probably some benefits related to nitrogen deposition some carbon deposition in some places. Now, what sort of would result from that, I'm not sure, but I think there's a lot more to talk about with that.
Yeah.
So wood burning, obviously the smoke effect and the aerosols can have negative human effects, but this is a mechanism for transporting nutrients, and particularly phosphorus and iron, that are very soluble in these particles when they fall into the ocean. And even in models today about aerosol impacts on marine productivity, there is a big differentiation between mineral dust and the anthropogenic burning aerosols, because they have very different solubilities and therefore different effects on ocean biology or wherever they deposit it, not only ocean, also in soil. A lot of the phosphorus and iron that falls in the Amazon River, Amazon basin, sorry, come from burning. So
Yeah.
there are positive natural biogeochemical effects for moving nutrients from one place to another.
Yeah, thank you. Oh,
Maybe I'll also quickly comment. I thought your question is very, very interesting, and I had to think about it while the other speakers were responding. Yeah, first of all, I think smoke and air pollution from fires has mostly been researched as like the health effects and the mortality from it. And I agree with Adina, there are like other effects from aerosols that are very important, and aerosols and the interactions with clouds also has like a climate cooling effect. So we often talk about the greenhouse gas emissions from fires and their climate warming, but there is that cooling effect from aerosols as well. And then something that I found very interesting when I was in Siberia in 2019, where there were a lot of big fires going on there. We were doing field work in one of the villages and being around there for a couple of weeks, and like we were all very concerned about the smoke. And then some people there, they just told me at some point, like, yeah, smoke for me, it means that it's summer. And I was like, oh, where does that come from? Like, to them, it's also something that is very natural that it happens, and it's just part of it as well. I mean, this is just anecdotal, but I just wanted to throw it in here.
Yeah, thank you so much. I mean, I think a lot of the answers that you provided kind of make me think about timescale, and that the human health timescales are very like singular. What's going to happen to me in my lungs, or versus ecosystem health timescales. And so, how do we? Thinking about fire research, and I think this comes to the nice sort of conceptual framework, Michelle, that you presented. There's a lot of similar questions, but there's this issue of timescale, and I think sometimes we just don't have that perspective as a whole or as communities. And so how do we work to try to change that? Maybe that's a very long discussion point. So I don't know if you want to think about that, but that was my second comment and question.
This may be beyond the expertise of the panel. I haven't been here the entire time, but regarding human health, I read something very recently that all of the burning and the fires and the aerosol and the material in the air has been linked to a marked increase in fungal infections in humans. Does anybody know anything further about that? It's something I'm kind of curious about. I'll just be honest, having experienced one and nobody knew what the heck it was, and for some time diagnosing all the wrong antibiotics, and so it turned out it was a fungal thing, and they finally treated it with the right thing. But then I read these articles just recently about that this was due to or scientists have linked that with wildfire products from wildfires. Does anybody know anything more about that?
I can share something that is not based on any paper, but based on some observations of one of my undergrad students who's collecting aerosols in Santa Cruz. And after the fire, he did see a huge increase in the number of spores on the aerosol filters, fungal spores. So they probably, I don't know for whatever reason, the spores are mobilized after the fire, or everything else gets burned and the spores remain. But there's definitely, we've seen more spores in our bioaerosol counts after the fires.
That's very interesting. I should add that I live in Colorado a good bit of the time, and lived through the terrible fires we had there a few years ago. So, but that makes some sense. I mean, after all, spores kind of rule the world. They've survived most everything.
Hi there. Oh, that's loud. My name is Brooke Newell. I am an undergraduate at Texas Christian University. I'm also from Colorado, and a couple months ago, my hometown actually got hit by a wildfire, but that's been kind of raising a lot of questions in my head about the chemistry of wildfires. So Dr. Newcomer, I was wondering if the different fires that you look at, ones that are more like predominantly burning urban areas and homes versus ones that are burning like more trees, have you noticed any sort of difference in the chemistry of like what's happening in the water or anything like that, if that's anything that you've noticed?
Yes, there are definitely differences, and I'll give you a few examples. In the counties of Sonoma and Napa in Northern California, we sampled for perfluoroalkyl substances, which are one of the main combustion byproducts from anthropogenic materials. And it's interesting, we found most of our higher concentrations in groundwater samples, but not in surface water samples. And so that somewhat confirms the conceptual model we have in our minds of how the hydrological system is functioning in that watershed, that groundwater is a really important store for these anthropogenic contaminants after fire. Another thing that we saw that was quite interesting was in the surface water, we saw increased concentrations of mercury. And so mercury can come from historical mining operations as well as from natural vegetation. It's found in the landscape naturally. And we found this increase in mercury during one storm event. So one storm event, we saw this major flush of mercury from many of the tributaries across the watershed. And we attribute it mostly to the natural combustion products, the soils, the vegetation. And we found that interesting because there is historical mining in the watershed, and we found similar concentrations across both the mining areas, the historical mining areas, and the natural areas. So for us, we found that very interesting result, and that it only occurred after the first rain event. After that first rain event, it was done. We had concentrations go back to historical levels. So those two things we found were quite interesting. Other things that we expected, things like nitrates. We didn't see increases in nitrate. We didn't see increases in sulfates or phosphates, which you would expect. Phosphates, for example, are coming from I'm forgetting the word for it, but it's the deposition of the fire retardants on the landscape. They have a special name. And you would expect to see phosphates, but we didn't see that. And so that also is what we're using in our conceptual model, that it's probably mostly stored in the groundwater at this point, and since we're not seeing it in the surface water. So we anticipate we'll see some increases in that in the next few years, which really raises the point that sometimes you think that the most important events are the first flush events after a fire, which they are. They're very important for the chemical constituents of concern. But for other constituents like, metals and nitrates, for example, that can take years to emerge. If you have major sources of that water emerging as groundwater to the river, then you can expect those to emerge 5-10 years after the fire. So for us, we're continuing our monitoring. We're now 6 years post-fire, and we anticipate in the next few years, if our conceptual model is correct, if we're correct in our thinking, that we'll see some of those increases down the road.
Thank you.
Thanks for that comment. I'm not surprised that you found the mercury raining down and in the catchments and riverine. Related to the same sequence of forest fires that I mentioned in Colorado a couple of years ago, being a curious scientist, we had so much ash falling on the top of cars and windshields that I went out with a few vials and picked up the pine needles that were burned, and then another one, birch, a whitish birch, looked at some of this on the SEM, but analyzed it for mercury, and there was nothing in it. Now, we all know it started out with something, and Colorado's a mining state as well. So that stuff took off, and what was left in the actual ash that rained down was beyond blank level, better than our blanks. So
I'll just make a comment quickly about the ash. The chemical characteristics of ash, that's an important research question. And I'll probably refer you to my colleague in the back of the room, Jackie, who can comment more on that. We're doing some research together in the Caldor area where we've collected ash to really examine that question.
Great. Hello. Thank you for the session. It's really very interesting. I'm based in Albuquerque, and so I've recently gone to the Hermit's Peak and Calf Canyon fire area. And we're starting to collect some geochemical samples and partner with you and University of New Mexico as well. So my question for this session would be, because of the fact that these controlled burns got out of control and that caused a lot of concern in the region, and they've stopped those controlled burns for now, it seems like another message that the scientists need to push is understanding how the controlled burns have helped prevent these massive fires over time. So do you know of good publications that have looked at that to see how controlled burns relate to the size of the fire versus a controlled situation in a similar area that didn't have controlled burns and how big they got, or something like that?
Well, I can't point you to papers off the top of my head, but a few of them do exist, but they're few and far between. And I think that's a real critical research gap, that these are opportunities. The prescribed burns, land management activities, thinning, crown fires. There will be a crown fire prescribed burn in Colorado in the next year. Those represent some of the best opportunities to begin investigations, not only for human health impacts, but also for these other impacts, to say what is required of a landscape to push it beyond its threshold for change, and what sort of fire severity and intensity and size will push it beyond its threshold to maintain its steady state. And that steady state of a landscape, we don't have enough information and baseline data to really say what that is. Now, I'm sure for many disciplines, ecologists, microbiologists, and hydrologists, they have their own perspectives on what does a steady state mean. And, you know, I think that's where the interdisciplinary research is required to come together to say, you know, this type of fire of this size, this magnitude, this is how we can maintain that sort of steady state that we think is best for the landscape.
And maybe a quick comment on like the temporal window that you can do prescribed burning, which I guess is, for example, in spring, when it's like still wetter conditions, but these windows are also changing because they're under pressure of climate change. So maybe sometime in the past you could still kind of start a prescribed fire, I'd say something at some point in the year, but now that may not be safe anymore. So I think you also have to account for this upward pressure because of a changing climate and adapting these policies.
That's a really great point, and it speaks actually specifically to the fires that were at fault for Hermit's Peak and Calf Canyon. That was one was the pile burn, and the other was a spring, an ill-advised spring, very hot, very windy, very windy prescribed burn. Climate is taking the spring burn window out of the equation in the Southwest, basically. We used to burn in the spring. I'm not sure how much longer or how easily we can burn in the spring anymore in the Southwest. I would point you towards some of the work of the scientists at the Ecological Restoration Institute at Northern Arizona University, who've looked at the benefits of thinning and prescribed burning in contexts like the Rodeo Sky fire in Arizona and a few others. There was a paper that I'm blanking on, Michelle might remember, I think that came out just this year about how thinning and prescribed burning have protected some of the sequoia groves from higher severity outcomes. It might be in fire ecology in the last 12 months.
We're almost done, so let's take our last question, and after that we have posters.
I just had a question regarding the prescribed burns that you mentioned, and the fact that they are a canopy prescribed burn. In Australia, my understanding of prescribed burns is that they are a low severity fire, so constrained to the understory. So I was just wondering how often in North America you're doing these crown and canopy prescribed burns, and whether you've noticed any trend between whether these are more likely to be the ones that become out of control, or whether there's no trend there, that this is something that is just a routine situation.
So from my own knowledge, in California, I don't think that there is very much taste for the crown fires that you're mentioning. However, the perception about that could be changing. And I'll mention the example of Colorado. There is planned a crown fire prescribed burn in the Upper Gunnison Basin, either next year or the year after. It's still in the planning process, but we're working with the U.S. Forest Service to begin to implement scientific activities to assess the effects of this crown fire that they're planning on the hydrology, on the water chemistry, on the landscape in general. So I think that depending on how that goes and how the public perceives that particular fire, I think that's going to inform how well this idea begins to take hold in other places.
Thank you.
Thank you, everybody, and let's thank our speakers again and say mahalo nui and